Hi everyone, and welcome back to Math 11. So in this chapter 8, we're going to be looking at proportional reasoning. Now proportional reasoning can kind of be in multiple forms. For example, one of them you can compare rates. Another place you might see this is you comparing sizes, or perhaps you're comparing weights or volume. You want to scale something up or you want to scale it down. So definitely going to see a lot of this in, let's say if you go into trades or if you go into engineering, you have to scale up things or scale down things all the time. And you're also probably going to find a lot of this is review from your grade 8, grade 9 math, where you kind of learn about scale and how you can scale things up, scale factor and stuff like that. So a lot of this will be review. So probably out of a lot of the chapters that we've learned this course, this is probably one of the most kind of application-based type of unit. So first, let's take a look at rates. So rate have two units. So you normally have something per something else. So for example, we have heart rate, which is 85 beats per minute, or the speed of a car could be 60 kilometers per hour, or in this case, price of ham is $1.99 per 100 grams. So all of these are rates. So different units, but all of these are examples of rates. Let's take a look at the first example. It says here that Natasha can buy 12-kilogram turkey from her local butcher for $42.89. The local supermarket has a turkey advertised in its weekly flyer for $1.49 per pound. And there are about 2.2 pounds in a kilogram, which store has the lower price. Now, I should tell you that you can solve this question in probably 3 or 4 different ways. Okay, you can convert pounds to kilograms, kilograms to pounds. You can look price per pound or dollars per mass, whatever. So there's more than one way you can solve this question. So I'm going to solve it in one way, and I encourage you that you read the textbook and look at the solution in the textbook and how they did it, because I'm going to do it a little different. So because again, there's more than one way you can do this question. Make sure you look through the textbook and see how else you could have solved this. So what I'm going to do is I'm going to convert pounds to kilograms. So then I have to compare the same type of units, because you can't really compare two different systems here, right? So the first step is to convert, let's say, the 12 kilograms to pounds, or the other way around in this case. So what I'm going to do is I'm going to use my my ratio, my scale factor here between the kilograms and the pounds. And let's see, we're gonna start with the price of the turkey at the store. So let's convert the pounds, so $1.49 per pound. Let's convert that to dollar per kilogram so we can compare it to the butcher. So we know that 2.2 pounds, so LB stands for pounds, is 1 kilogram. So I'm going to write 1 kilogram across from 2.2 pounds. And then I know that I want to know how many kilograms is 1 pound. 1 pound. So this is going to be my X. This is going to be my unknown in kilograms here. So we have to cross multiply here. Okay, so X is going to end up being 1 times 1 divided by 2.2. So 1 times 1 divided by, in this case, 2.2. So this is just basic cross multiplication, which means that 1 divided by 2.2 is 0.45 kilogram. So for the supermarket, we have the following. We have that $1.49 per pound. Now we know that it's going to be $1.49 per 0.45 kilogram, because we just figured out how many kilograms is 1 pound. So we know that this is going to be the $1.49 per 0.45 kilogram, which if you actually do the math here, you end up with $1.49 divided by 0.45 is going to be $3.3 dollars per kilogram. All right, so that's our supermarket price. So the butcher, he sells 12 kilogram turkeys for $42.89. So how do you compare it? Because again, we're not told the price per kilogram. We're told the price per 12 kilogram turkeys. So for the butcher, let's take the total price of $42.89 and divide by the mass of the turkey, which is 12 kilograms. So again, you're going to end up with dollars per kilogram. So when you do this, you get a price in dollars per kilogram. So we get 3.6, let's write the dollar sign in front, dollars per kilogram. So as you can see here, now we can compare these two, that we have the same rate. We have dollars per kilogram, dollars per kilogram. Like I said, you could have done this in other ways. You can compare dollars per pound to dollars per pound, right? So this is one way that you can solve this question. And as you can see here, the butcher is slightly more expensive. It's 3.6 compared to $3.3 per kilogram to the supermarket. So perhaps it's fresher, maybe it's better quality, maybe it's organic, I don't know. So anyway, the butcher's slightly more expensive. But anyway, in this case, the goal of this question was to compare them and figure out which one's the lower price. The supermarket is the lower price, so you can say that the answer would be supermarket has the lower price. That's normally the case. Smaller businesses usually have slightly higher prices. But anyway, what we found here is the unit price. Okay, so in this case, I should make a note here. In this example, we found the unit price. Okay, so unit price means that, or unit rate, in this case, the general term would be unit rate, but because we're talking about money, this is the unit price. So this means that we found a rate in which the value of the second term, which in this case, the first term is our dollars per kilogram. So if we look at the terms here, dollars per kilogram, this is our second term. This is our first term. Right? So the second term, the kilograms, is going to be per 1 kilogram. So if you look here, I did not write 1 kilogram, I just wrote kilogram, but that just means that's per 1 kilogram. You can actually write a 1 in front of it, but it's not really necessary. But that means that it's the dollar amount per 1 kilogram. So that's what makes this a unit rate, or in this case, a unit price, because it's dollars per whatever item, per kilogram in this case. All right, so what else can we do with unit and rates? So let's take a look at example number 2. Now, example number 2, we have this diagram, which is distance versus time graph. And it says, describe a scenario that could be represented by this graph, compare the rates shown, and discuss why the rates may have changed. Now, because we have time over distance, time over distance is speed. So this graph represents the motion of some object. So perhaps it's someone running or driving or maybe biking or something, I don't know. So we had to figure out what the speed is, then to have an idea what this could mean. Now, because you're given a graph, what we're going to do is we're going to compare the rate. And in order to compare the rate, we have to look at the slope of the line. Now, because this is Math 11, we can look at the graph and find the slope quickly just from the graph. Because especially if you already have a graph, that's the quickest way. It's just to look at your graph, find the change in y, change in x, and then find the slope. Remember, slope is going to be the change in height or change in y over the change in x, or rise or run. So remember, rise over run. That's the definition of slope. Now the delta y, delta x is just a quick way of saying change in y, change in x. So delta means change in something, so final minus initial. Now if you want, you can expand this. You can say that delta y is going to be your y2 minus y1 over x2 minus x1. It's not really necessary in this example because we have a graph. If we didn't have a graph, we're given values in a table of values, something like that, then you might want to use the equation. Otherwise, you can just use the graph to find the slope. So before we find the slope, first let's break it into different parts, because as you can see here, we have different steepnesses here. So let's break it apart into first part. So I'm going to use Roman numerals here. Second part, third part, and then the remainder here is going to be our fourth part. All right. So in order to find the slope, we need the change in y. Now from the graph we can see here, so let me use different color, that the change in y for the first part is going to be 2 units of distance over 1, 2, 3, 4, 5 squares, 6 actually, of time, which corresponds to 30 minutes. Okay, so for the first interval, okay, we have our change in y over change in x. In this case, we're talking about change in distance in our y. So this is going to be our delta d over delta t for time. Okay, that's what we're doing for part 1. We're going to do 2 units, which is measured in kilometers in this case. So we have 2 kilometers over 30 minutes. Okay, so that's our unit rate, or our rate here in the first interval. Now, kilometers per minute is not really a usual measurement for speed. So let's convert kilometers per hour, because kilometer per hour is probably the most common unit that we use, at least here in Canada. So we know that there are 60 minutes in an hour, so all we have to do here is to get rid of the minutes and change this to hours. So we know that 1 hour has 60 minutes, so minutes has to go on the top, and hours has to go on the bottom. So there are 60 minutes in 1 hour. So that just means we had to multiply our answer by 60 to get the speed in kilometers per hour. So in this case, 60 and 30 is simplified to 2. 2 times 2 is 4. So we get 4 kilometers per hour here. Or you can just use a calculator if you want. All right. So there you go. That's our speed in the first interval. So 4 kilometers an hour. So that seems like someone may be walking fairly normal rate, I guess. It's not really fast. 4 kilometers an hour is kind of walking speed. So let's take a look at interval number 2. So number 2, if we look at interval number 2, the line is horizontal. That means that there is no slope, means there is no rise, there's only run. So in that case, if there's no delta d, we only have delta t, which means we get 0 over, in this case, 10 minutes. From 30 to 40, that's 10 minutes, which means this is 0. Well, if this is minutes, kilometers per minute, doesn't matter what the units are, still going to be 0 in kilometers per hour. So we can say if this is 0 kilometers per minute, this is also going to be 0 kilometers per hour. So in this case, it's pretty easy, per hour. All right, so there you go. We have our speed for the second interval. Let's take a look at the third interval. So again, we're looking at delta d, change in distance, over change in time, delta t. So for the third interval, we have a positive slope here. And let's see, here we have, we can make this right angle triangle here, right? So we have 1, 2, 3, 4. So that's from 40 to 60 minutes. So that's going to be 20 minutes for our time. And for the distance, we went 1, 2, 3, 4, 5, 6 squares, but it's every 2 squares that's 1 kilometer. So that's 3 kilometers in total. So we're going to have 3 kilometers over 20 minutes. All right? So that's what we have in third interval. So let's take these 3 kilometers per 20 minutes and change it to kilometers per hour. So 3 kilometers per 20 minutes. Convert this to kilometers per hour. So again, you want to get rid of the minutes, so minutes have to go on top. hours have to go on the bottom. So there's 60 minutes in 1 hour. So 60 divided by 20 is going to be 3. And 3 times 3 is going to be 9. So we're going to get 9 kilometers per hour in this case. All right, so we have 3 intervals already. Let's get the final one. Now the final one looks like someone is going back, because it started from 0 and went all the way up to 5 kilometers and then returning back quite quickly here. So the time for this 60 is right between 60 and 70, which means that's only 5 minutes in time. All right, and the distance, if we look at the distance, it goes from 5 to 0. So this is going to be negative because the slope is negative. So our delta D here over delta T is going to be negative distance negative 5 kilometers over 5 minutes. Now you can have negative speed. If we actually talk about displacement, which is actually a vector quantity, which cares about the direction. So in this case, the negative indicates the direction. So this is probably velocity, which is actually a vector, not a scalar value like speed. But anyway, in this case, the negative just means they're going back to where they started from. So nevertheless, we can calculate what this is. So we have, let's see, we end up with negative 5 over 5, which is 1 kilometer per minute. And then we can convert this to kilometers per hour. So let's take the 5 kilometers over 5 minutes and multiply by our conversion factor, 60 minutes per 1 hour, right? So minutes and minutes go away, same thing as in all of the previous. We're left with kilometers per hour. So in this case, we end up with negative 60. So let's take a look at the speeds here and think what could have happened. Let's say if this was a person that, this whole thing occurred. That's part of the question. It says, describe a scenario that could be represented by this graph. So 4 kilometers an hour, that's the walking speed, right? 9 kilometers an hour, that may be like someone is jogging or running. And then 60 kilometers an hour means that someone took perhaps either like a taxi or drove a motorcycle or a car or took transit or a train or something back to where they started from. So this could be someone who went out for maybe a jog. They jogged for the first 30 minutes, right? So the first 30 minutes at 4 kilometers an hour, they took a rest for 10 minutes and then they run for 20 minutes at 9 kilometers per hour, and then maybe they got to a bus stop and took the bus back to where they started from. So in this case, the negative 60 just means that they returned, so they went in the opposite direction. So this negative means went in opposite direction. So if you take physics, you're going to learn about vectors, you're going to learn about velocity, the difference between velocity and speed. In this case, this represents actually velocity, not speed, because we have direction, which in this case is indicated by this negative. So again, you could have described this as someone jogging, or actually here, like probably walking. Okay. Here they took a rest. So they stopped. To rest, I'll just say to rest. Here they maybe they ran, so let's say running. And here they took a bus home. Took a bus or a taxi to the starting point. That would be more accurate. All right, so that'd be one example. So in this case, again, we're comparing rates based on the graph. So in this case, you're given a graph. So let's take a look at the last example. So in the last example, we have a table of values. So the question says, when making a decision about buying a vehicle, fuel efficiency is often an important part or factor. The gas tank in Mario's new car has a capacity of 55 liters. The owner's manual claims that the fuel efficiency of the car is 7.6 liters per 100 kilometers on the highway. Before Mario's first big highway trip, he set his trip meter to 0 kilometers. So his odometer, trip odometer, which measures the trip distance. So he reset it to 0 kilometers so he could keep track of the total distance he drove. He started with the gas tank full. Each time he stopped to fill up the tank, he recorded the distance he had driven and the amount of gas he purchased. So if you have fairly, I couldn't say old, maybe like 10-year-old car, chances are they didn't have like infotainment systems like they do now, which keep track of fuel efficiency. Some of the cheaper cars still don't. So some of the newer cars definitely already have that all built in, but back in the day, for the last 100 years, people had to do this by hand if they wanted to know their fuel efficiency. So we have a table of values. We have one fill up, the first fill up, which was after driving for 645 kilometers. And it says here that he purchased 48 liters of gas. So he used up 48 liters and drove 645 kilometers. And then on the next one, the next stop, the trip odometer, the distance that they've driven is 1,037 kilometers, and they've purchased an additional 32.1 liters, which means that from 0 to 645, they used 48 liters. And then we had to figure out what was the distance at the second fill up. So this would be the 1,037 minus the 645, which would equal, let's see, that equals to 392. So on the second fill up, they drove for 392 kilometers and they used up 32.1 liters of gas. So it says, on which leg of Mario's trip was his fuel efficiency the best? Well, fuel efficiency, again, can be compared in different ways. You can compare liters per kilometer. You can compare liters per 100 kilometer, which is kind of the units that most countries use, except for US, where they use gallons per, I don't know what they use, gallons per mile, something like that. I don't know. That's some weird imperial unit. But anyway, we can compare it either liters per kilometer or liters per 100 kilometers. So for the first leg, we'll have to use basically the definition of slope again. So in this case, we have, we want to know liters per kilometer. So this is going to be our volume. So this is liters, right? So this is our, let's say, volume 1. So V1 for volume, V2 for volume 2. And this is going to be our distance 1 and distance 2. So first leg, we're going to look at, so again, fuel efficiency. Is going to be the gas that you use per distance traveled. Okay, so that's what we need to know in order to solve this question. So for the first leg, let's plug in the values for the gas used. We know that we've used 48.0 liters. That's the volume that we used. So 48.0 liters over the 645 kilometers. Now, if you do the math here, this ends up being 0.074 liters per kilometer. Now, it's really important to keep the units with this because that kind of tells you what you need to do later on in the question. So I do keep the units in this calculation here. Now let's do the second leg. So for the second leg, we're going to do the same thing when I calculate the fuel efficiency, which is going to be the gas used over the distance traveled. So this is going to be, so this was, first of all, this was our V1 over D1. Now we're going to look at V2 over D2. So our second volume of gas is 32.1 liter, and the distance was 392 kilometers. Now, in this case, this equals to 0.081 liters per kilometer. Okay, so far so good. We have our two rates for each of the legs of the trip. Now let's take a look at our fuel efficiency. So the user manual, which is normally not really the place that you look at efficiency. Usually people review the cars, not the manufacturer. So, but anyway, regardless, we have our value to compare to. Now, from here, we can already answer the question, which leg was more fuel efficient? Well, the leg that uses the less amount of fuel per kilometer. So in this case, the first leg, they used, Mario used less gas. He used 0.74 liters per kilometer. In the second leg, he used 0.081 liters per kilometer. So he used more liters of fuel per kilometer. So already we see that the second leg was lower fuel efficiency. Okay, but anyway, we had to compare to this unit right here, 7.6 liters per 100 kilometers. So we had to convert our two units to liters per 100 kilometers. So that's pretty straightforward, actually. It's not that complicated. So let's do a couple of calculations here. So let's take our, again, first calculation, which was the first leg, 0.74. And this is why you want to keep the units, because the units will tell you what you need to do. Now, I want to have 100 kilometers on the bottom. So all I have to do here is, if you multiply by 100, right, this will tell you the rate of liters per 100 kilometers. So if I do this, multiply by 100 kilometers, if you notice, the kilometers and kilometers will go away, and you're going to be left with the volume that it took to drive 100 kilometers. So the value that you're going to get here is actually going to be the value of liters of gas that took to drive 100 kilometers, or the amount of fuel per 100 kilometers. So in this case, we're going to get 7.4 liters for the first leg. Then for the second leg, we're going to do the same thing and multiply 0.081 liter per kilometer times 100 kilometers. And again, kilometers and kilometers go away, so you're left with just the amount of fuel in liters, and this equals to 8.1 liters. So that's the volume of gas per 100 kilometers traveled. So as you can see, now we can compare it to the value that was stated by the user manual of 7.6 liters, right? So 7.6 per 100 kilometers, we're getting 7.4 and 8.1. Well, let's compare it by taking this and taking the average. So let's take the average and see if it matches our user manual. So let's do 7.4 plus 8.1 over 2. So our average ends up being 7.75 liters per 100 kilometers. So that's what we end up getting. So the first, or the question was, which was the best leg of his trip? The first one, this is the best. And then just to see if their claim was true, we did this conversion, which is not well what the question asked, but just to see if it was actually true or not. So because he was driving on the highway, his fuel efficiency was 7.75 liters per 100 kilometers. The user manual claims to be 7.6. So that's pretty close. It's 0.1 units off, or 0.15 in this case. But it's fairly close to what the claim is to be. So that's not bad. That's fairly efficient. So again, make sure you read the textbook, because like I said, a lot of these questions can be solved in more than one way. So read through the solutions and see if you maybe like the other way of solving this question better. So it doesn't matter how you solve it, as long as you show the right steps and you understand what you're doing. So for practice, make sure you, this is chapter 7, So we're doing mathematical proportional reasoning. So hold on, proportional reasoning is way down here. Scale models, proportional reasoning, so that's chapter 8. So 8.1, make sure you read pages 452 to 458 and do number 1, 3, 6, and 13. Again, if you have any questions, make sure you post them as a comment in Teams.